start and try to. Okay, so we've accomplished a way of starting this presentation. So round of applause, maybe. So intro to DP with OpenDP. We have this is for people who are new to DP, but then it's going to transition more into more technical details as we go. Can I get a raise of hands of how many people are completely new to DP? All right. Okay, so a lot of this talk is going to go over APIs and like how you actually make some DP releases. But before we get into that, we're going to do a like a what is differential privacy, kind of setting the groundwork for this. And then we're going to see the DP Wizard application. And then we're going to switch into kind of code examples of the core library. All right, so what is differential privacy? It's a definition of privacy. It mathematically quantifies how much a data release can reveal about any one person in your data. So we're trying to come up with a system, a mathematical system that will limit how much the answers will change if any one person's data is different. So data releases can be all sorts of things. They can be descriptive statistics like counts and sums, means, quantiles. You can incorporate grouping, as I was talking about in the previous presentation. You can build machine learning models out of it. It's just, in some sense, just another kind of descriptive statistic that you're releasing lots and lots of times. There's also synthetic data is something you can release with differential privacy. And you can build statistical models like linear regression, logistic regression, decision trees, PCA, and so on. So long as the kind of thing that you're
share your screen or share the link to the slides.
Oh. Can you get sharing? Oh, yeah. Okay, so do we have liftoff now?
Yes, you can see your slides.
Fantastic. Okay, so you can list anything with differential privacy that, for one, has some limit on how much an individual contribute to the data. And there's different notions of that. And for two, kind of aggregates the data in some way. You want to use differential privacy to describe properties of a large population. You don't want to use differential privacy to release pieces of information that could be specific to individuals. It's differential in the sense that this is a technology that obscures the difference between data releases on data sets that differ by one person. It says it doesn't matter which two data sets you pick that are differing by one person. You'll still get this guarantee that you can't tell from the outputs whether you're working with one data set or the other. You can't tell from the outputs that a given person was in the data set or not. So why do we use this definition of privacy? A couple reasons. First off, it's meaningful. It protects every individual in the data. It's robust against any adversary, potentially with unbounded computational resources, and it's immune to auxiliary information. This is like if the adversary is coming to your system with a bunch of information about an individual they want to attack, that doesn't give them a greater advantage towards attacking an individual in your data. It's also quantifiable. So what does that mean? It's got bounded privacy loss. So it doesn't matter what kind of query they ask. The kind of amount that an individual in your data suffers is limited. It's also mathematically rigorous, and it allows for interactivity. So you can go back to the data several times and make more releases. And the way the privacy degrades is kind of linear, typically, in that the adversary is not kind of getting super linear or like an exponential increase information as you get more and more, share more and more with them. So the privacy guarantees degrade nicely as you ask more queries. So how is it typically applied? Well, you're adding a small amount of random noise into statistical computations. And oftentimes there's some careful application of data preprocessing. You might clip your data within a certain range before you compute a statistic, or you might truncate the data in some way. We'll get some examples of that later. And sometimes the researchers get a little crazy and they completely replace the algorithm with something else that gives you better utility than you would have gotten otherwise. So when it's implemented correctly, it's the algorithm, the estimator, the mechanism, the measurement, whatever you want to call it, itself that can be shown to satisfy differential privacy. And you say that anytime that I shove data through this mechanism, the outputs I get will have only a limited impact from any one individual, a bounded privacy loss per se. So an example of an algorithm is just for a count. It's one of the simplest DP mechanisms. You just compute the number of records in the data set and add noise from the whole loss distribution. So it doesn't have to be complicated. Sometimes statistics are surprisingly simple. The methods are surprisingly simple. So the privacy loss of sharing the outcome of the algorithm, it depends on how many records the individual can contribute to the data. So if we're computing a count and we know that each individual in the data will only appear in the data once, then you add a certain amount of noise and it gives you a certain privacy guarantee. But maybe if it's possible they appear multiple times, then more noise is necessary to obscure how much that individual could affect the count. Through the library, you can kind of define how much an individual can influence the data set and what the privacy guarantees should be. And the library will go and solve a bunch of math and find out how to calibrate the noise to satisfy what you're asking for. So I'll go for a little live demo of DP Wizard because feeling maybe too adventurous today, especially after all those technical issues we got started with. So DP Wizard is it's a GUI for kind of exploring and building an initial DP algorithm with a library. So I'm going to start with just saying we're going to work with a hypothetical data set that has two columns in it, A and B. Light mode. Notice that there's a lot of blue text here. This is just kind of explanatory contextual text for each of the options, or you can just go raw and drop those. But if this is the first time using differential privacy, it can be really helpful to read through these and help guide the choices you're making. So I've just said that in this hypothetical data set, we have two columns A and B. Um, uh, so kind of going off into the application of a deeper topic. In practice, you need when you implement differentially private algorithms on computers, finite computers like we all have, there's kind of a difficulty in dealing with random rounding when you're adding up floating point numbers and potential overflow and the intermediate calculations. And so we found that if you can just specify an upper bound on how big your data set can possibly be, then we can account for all these things. Oh, yeah.
So that looks more like a GUI interface, and when I was looking at the OpenDP wizard thingy, it looks more like it's just like a mainline interface. Is there like a pretty version that is accessible, or?
Yes. It's actually. If I hide this thing.
This is just part of it. You know, the GitHub is also the same. Like I could install this in like mainline or just various tabs.
Yeah, if you like pip install DP wizard, and then you like run like one command to start the website, then you can like run it locally in this nice GUI interface.
I just launched the logo.
Localhost, yeah.
Okay, cool.
Yeah, and there's also a cloud hosted version that if you go to the repository, you get a link through to it. Okay, so we're also going to define a unit of privacy, and this is what we're protecting. This is we're saying a unit of privacy is describing the greatest influence that one individual may have on your data. So we'll say that this is a pretty simple example. We'll say that if one person is added to our data, then it's going to add at most one row to our data. All right, and then we can go over to the second page. We're defining the kind of statistic that we want to run and release. So I'll say on column A, and if we group by column B, we can release, let's say, a mean. And we're going to use an epsilon of, I can tune this around 0.5. We're saying that this is the greatest amount an adversary can be advantaged by viewing this differentially private mean that's released from this algorithm we're building up right now. So in this setting, it's asking us for some additional information to quantify the statistic. We, in the case of the mean, you need to set a lower bound and an upper bound on each of the entries in your data. So this is to limit how much an individual can influence the sum and part of the mean calculation. So I'll say this is bounded between 0 and 100. There's a bias and variance trade-off here. So when you make the bounds wider, individuals can influence the statistic more, which means that more noise is necessary to release the statistic at a certain level of privacy. But conversely, if you make the bounds too tight, then you're going to introduce bias. The statistic is going to be, you're going to be kind of cutting off upper bounds or lower bounds of valid data, and it's going to cause the resulting sum to be like either too small or too large. So this is kind of a sensitive thing. You want to use prior information, kind of like domain expertise to inform your choices of these bounds. If let's say instead of column A, it's a column age, I might say, okay, well, clipping bounds could be 0 and 100. Most people aren't going to be more than 100 years old. So reasonable prior that we can incorporate in the building of a statistic. Any questions on this page? So you can download results. The main thing I'm going to point out here is you can download the notebook, and I've pulled that notebook up already. And what you get is a bunch of starter code for you to kind of mingle with and adjust to release the statistic you just read. I think it'll be a clearer exposition if I switch back to the slides to explain this stuff, though. Any comments on that? Is it clear what we're aiming for here in the DP Wizard application? I'll say for a little bit more context, it can run in two modes. There's a cloud version and there's a local version. And in the cloud version, this is what I was interacting with, and it's available for anyone to just access in the browser. You can't upload data, but you can upload, you can say which columns in your data, and you can kind of extract this sorter code. And in the local version, you can actually put your sensitive data in, actually make the release. All right, so diving down into the library itself. If you want to install the library, use pip install OpenDP. And I've included MBI for the contingency table functionality. Our example data set is this labor force survey macrodata. What I'm doing here is I'm loading up the data in a lazy way. I'm not actually accessing the data yet. I'm just saying, here's what the data is. Then the columns that you might be interested in this data, we have sex, age, ILO-stat, usual number of worked hours, quarter, and year. ILO-stat is kind of labor status. It's describing if you're unemployed or if you're employed, if you're self-employed, and so on. Okay, so the core API of the OpenDP library, especially for beginners, is this context API. And what we're describing here is three things. We've got the data, we have the privacy unit, and we have the privacy loss. So as I was saying before, the privacy unit is what our protected change is. In the labor force survey data, we have 9 years worth of data. It's collected on a quarterly cadence. So, and each time the survey is collected, each person can be a respondent only at most once. So, ergo facto, we have 36 contributions in the worst case. We also have a privacy loss argument. This is the greatest privacy loss that any one individual in your LFS survey data may be subject to, may suffer from. In this example, we're choosing a default value of epsilon of just 1. And in this setting, it's a good starting point for central DP with aggregate statistics. So at a higher level intuition on what differential privacy is that it's a certain kind of constraint on the stability of a function. So like just ignoring all the differential privacy stuff for a moment, functional stability is this property that, given that you have a bounded change in the input to a function, you also know that the output has a bounded change. So if you're familiar with kind of like Lipschitzianness, then you might be familiar, but we're basically saying if we know the input can change by only so much, then we know the output can change by only so much. And differential privacy is like a very specialized formula of this stability property. So we're saying the input can only change by at most the privacy unit. Therefore, the output can only change by at most the privacy loss. And an adversary is kind of limited in how much they can tell about any one individual, given that the privacy loss is bounded. Any questions on this? That's kind of a high-level intuition for differential privacy, and everything else from here is just trying to simulate APIs that we're familiar with from existing data science libraries, and hopefully reducing the amount of kind of DP extra complexity and overhead from here on. So what is this query doing? We have for this release, we're saying that the privacy loss can be only at most 1/5. It's epsilon of 0.2. And what we're going to do is we're going to release the differentially private length. And this is coming from the prior slide, so I'm going to kind of skip through it quickly. But in this case, given these parameters, the accuracy, the true value can only differ from the differentially private estimate by at most 540 with 95% confidence, because it's set our statistical significance to 0.05. And when we release this, we get our differentially private estimate. So on the DP Wizard interface, there was this option to set an upper bound on how big the dataset can be. It's showing up now because we're computing a DP sum. So I'm going back to the context and I'm adding this margin that says dataset size can only be this big practically. You can set really conservative upper bounds if you're not sure how big the dataset can be. The penalty is relatively weak for overestimating it. So I'm showing you a bad practice already. The best practice is to only ever make one context and submit all your queries to it. But I'm going to be kind of making multiple contexts throughout this talk to show different settings of the library. So this is what a DP sum query looks like. I'm also adding some extra pre-processing. It turns out that the usual number of worked hours, for some reason they've encoded like an invalid answer as 99, and we don't really want to include that in our sums. So we're filtering. We're selecting this this column. We're doing a cast to ints, and then we're computing the sum. We're going to get the total number of worked hours. We're saying that naturally, most people won't be working more than 80 hours a week. Maybe it's possible someone works more, and we're introducing some bias here by clipping the upper bound to 80. But the goal isn't always to make sure that you have zero bias. It depends on your use case, and it might make sense here to choose a more conservative clipping bound to reduce the noise that's added and overall reduce the error. All right, so I'm just showing another summarize table output. In this case, we're adding enough noise where the accuracy looks really bad. It looks like we're adding a lot of noise. But given the scale of this data, this looks like a large absolute number, but it's a really small relative number. So keep that in mind when you're kind of evaluating the utility of these things. remember we had like 3.8 million people in the data. So adding noise of like 14,000 is gonna kind of be washed out by uh, just the scale of the data. We also have a example of a DP mean. All I did here was swap the sum to a mean, and it's going to work out how to split your budget amongst a sum and a length query. We get separate confidence intervals. We can build separate confidence intervals for each of those. Unfortunately, mathematics decided that we can't build confidence intervals for the ratios of two random quantities very easily. So this is what the universe has deemed. So since what it's doing is it's computing a sum and a length, and then it's just telling you what the ratio of those two are, maybe you instead want to release those separately, and then you get an estimate of both quantities that you can use on its own. Maybe you're computing a bunch of different sums over different columns. You could just estimate the size of the data set once and estimate sums for each of the columns, and then build your DP means from all those instead of re-releasing the length multiple times. I don't have I didn't see a lot of hands for prior experience with DP, so I'm not going to dive into bounded DP. We also have an example with DP quantiles. So in this case, we're building multiple queries in the same in one shot for the 0.25 quantile, the 0.5 quantile, and the 0.75 quantile. And when I build this this query, I'm breaking my budget up amongst these multiple smaller statistics. All right, so difference in perfect grouping. It's a really common thing for data releases. There's two primary approaches for going about this. Either stable keys or explicit keys. So stable keys uses this algorithm where you group by some column of interest. Maybe I'm going to group by the ILO-stat employment status, and compute the number of records in each bin in a differentially private way. And I'm only going to keep bins where there's lots of respondents. And the thinking here is that we don't want to possibly release a bin that is unique to an individual. That could be sensitive information. But if a bin is shared amongst many individuals, like there's many individuals who have this I am employed status, then it's not sensitive information. This is kind of well known. There is a downside here in that it costs an extra privacy parameter delta. This is well, in this setting, it's a probability of failure of releasing a bin that is unique to an individual. And so this is why the choice of delta is always so incredibly small. We're choosing choices of delta that are like cryptographically small, like 10 to the negative 9 or 10 to the negative 8 to reduce the probability of potentially releasing a bin that is unique to an individual. A second approach is explicit keys. So we're saying we know what the employment statuses are ahead of time. I'm not going to try and release the keys privately. I'm just going to do the aggregation when grouped by ILO-stat. And then I'm going to do a join against this public key set. And I'm only going to keep records that are in the public key set or groups in the public key set. And if there's any values in my public key set that don't exist in the data, I'm going to convincingly replace it with 0, like a noisy 0. So let's say we group by ILO-stat there's this category 4, there's no respondents in it. We can't just tell the adversary that nobody responded with a given category. That could conclusively tell you that your neighbor isn't in that category, or isn't in that category. So what we do instead is say, well, there were 0 people in that category, and we add some noise to it so that you can't really tell if there were 0 or not. There's some plausible deniability there, and when you kind of math it all out, it works to satisfy the definition of privacy. An adversary can't tell if that key existed or not in the original data. So these are our two approaches. A nice benefit of specifying the keys explicitly is that there's no extra delta privacy parameter. There's no probability of failure. So you get a stronger guarantee of privacy here.
Does for the explicit key, like, does that value change? If it's 0 sets, if it's like, this job description has none, this job description has none, are these variable between those, or is it kind of the same number? Because it's kind of infer membership by the fact that like the number is the same. You'd be like, oh, okay, it's 0.16.
Well, so every bin that has no respondents is getting a separate application of noise. Yeah. Okay, so how does this look like? How would we actually group with stable keys and get some tables out of this? We're going to build a compositor with an allowance for this extra privacy parameter delta. In this case, I chose 10 to the negative 7. And then down below, I group by, in this case, age and ILO stat, and I get when I summarize, I get this additional column in the table saying that any bin with fewer than 3,458 records in it is going to be dropped from the data. There's a kind of a high standard there where you really have to have a lot of contributions from different people in order to make the bin show up in the output data. Any questions on this before I hop on? So now here's an example with explicit keys. What we're going to do is release another query. This time we can say delta is 0. There's no probability that this might fail. If maybe this time I want to go back and release the sum over worked hours. I'm actually reusing the keys released in the prior query, the stable keys, to set an explicit key set in this next stage. So the big difference in the API between the two is just this presence of the .with keys row. If you specify what the keys are, then the library is a little bit more forgiving about your privacy parameter delta. It can be 0. And then with a library, you can do more than just grouping an ag. You can build new columns before you do that. In this example, I'm building a new column with bins of the usual number of worked hours at certain cut points. And then I'm grouping by this bin data. It's shadowing the column when I do the cut and bin. You can also embed that into the criteria for the group by. So this is the exact same computation as the previous slide, but these kind of stable transformations of your data can be applied in different places. And we support a lot of different kinds of preprocessing, a lot of different data types, ints, floats, strings, bools, categoricals, enums, date times, times. There's a fair amount of Boolean logic, binary express operations. The limitation here is that we want to go case by case through different operations that an analyst may run, and check to see if it satisfies this stability constraint. If a change to the input is a limited change to the input still results in a limited change in the output. So we kind of go through each of the possible dataset preprocessing operations and write proofs and show that it's not going to when you apply this transformation to your data, it's not going to change the outputs that much or a bounded amount. Any questions on that before I hop on? Okay. So user identifiers. This is a setting where an individual might make an unbounded number of contributions to the data, but every contribution they make shares the same identifier. This comes up a lot of the time with data sets where you've got event level data, or maybe you're collecting data at a regular cadence, and the same respondents may be present in multiple times. And the difficulty with this is that since you don't know how many records an individual could contribute, well, you start rubbing up against the pessimistic natures of DP, where DP wants to consider what's the worst possible case. So if you don't know what the worst possible case is, then the DP literature comes back and says, no, you can't do it. You can't release anything, and it will be private. So we have this this method where we can limit the number of contributions an individual makes to the data through truncation. And what this is doing is it's literally just dropping any records from an individual that appears more than some predefined threshold. So the predefined threshold is something that, like the clipping, has a bias and variance trade-off. You might say, for the zero stat data, it's in the worst case, someone could show up 36 times, but who's going to respond to a survey every quarter for 9 years? Like, practically no one's going to do that. So like you could say, well, actually, it's really unlikely that someone responds more than, and I'll give it a big number, 10 times. If they respond more than 10 times, then we're going to discard any more contributions they make, and it's not going to affect our outputs. Right. So this is what this line is here doing. So only keeping at most 10 records from an individual. We've made this adjustment to the privacy unit up here. We're saying that the column that describes who contributed the data is the PIDent column. And then down below, we'll limit how many records they can add to the data. Afterwards, if you compute the means as we previously did, you get nice bounds. So you notice that before we were considering the worst possible case of 36 contributions from a user. Now we're saying, well, practically people aren't going to contribute that much. So we're keeping at most 10. And that results in a nice improvement in the utility. We'll have to add less noise to satisfy the same privacy guarantee, because we know that people don't add as much to, each person doesn't add as much to the data. But then practically it doesn't affect the bias. It doesn't introduce bias because for the most part, people aren't contributing that many records in the first place. So what I'm doing here is doing the same thing in a group by instead of using truncate by group, I'm using group by and then ag, and then I'm going to do a select or a group by afterwards. And a nice benefit of this is that for some statistics like the mean, what you can do is you can say we're going to group by the user identifier, and then in each group I'm just going to compute the mean. So we're going to get the mean number of worked hours per person. And then I'm going to, with this resulting data set, compute the mean over that. And so now in this setting, each person can contribute at most one record after we've done this pre-processing stage. But that record is the mean of all their contributions, so it kind of preserves some information from all the records that user contributed. And then we're going to give you the mean of that data set afterwards. And we get an even better utility from this. So the truncation bound was 10 before. And that resulted in a kind of a noise scale for estimating the length of 100. And now the noise scale is just 10. So we've got another 10-fold improvement in reduction in the noise added. And then you can do similar things if you're also grouping by afterwards. So in this case, we're going to, instead of just truncating the total number of records, we're going to truncate the total number of records per quarter. And we're going to truncate the total number of quarters that a user contributes. After all this truncation, we're going to group by the quarter that the respondent was in and computer statistics. So there's some nice utility benefits you can get from breaking things down like this. So these examples have all been in terms of pure differential privacy. There's another notion of differential privacy called zero concentrated differential privacy. And it's a weaker definition of privacy, but it allows you to do some cool things, especially in this setting. If you know that your contributions are spread out over many different bins, you're going to affect a lot of bins in a small amount, then the amount of noise that's necessary to add under zero concentrated differential privacy with a different mechanism is actually a lot less. It works out to like a square root of what it would be. So I'm kind of I'm pointing out a lot of practical things that arise in the application of DP to a problem. There's some cool tricks you can use to really reduce the noise if you know where to look. So I was talking about zero concentrated DP. The way this looks earlier when we're setting up the compositor is replacing epsilon equals a number with a rho equals to a number. And then internally, all the algorithms switch as appropriate. So if I rerun the previous query, this time under ZCDP, the noise scale will get even smaller. It depends on your choices of row at the beginning, but you'll get this nice benefit I was talking about, where less noise is necessary in the settings where you're asking queries that result in contributions spread out over lots of different bins. So here's kind of visualization of the different mechanisms. There's Laplace noise and there's Gaussian noise that we're adding statistics. In the case of Laplace noise, it's this more spiky one. When you're asking a small number of queries, it oftentimes has better utility than the Gaussian mechanism. So we're just kind of going through trade-offs of the two mechanisms. But when you're asking a lot of queries, it's often the case that the Gaussian mechanism is a lot better. You end up introducing less noise to get similar privacy guarantees. But a downside of this Gaussian noise is that since the tails decay in the way they do, you actually find that you need a weaker definition of privacy. There's like the Gaussian mechanism is valid under approximate differential privacy, not under pure differential privacy. And there's a way you can translate between zero concentrated to approximate. Maybe too much detail. Another one of the benefits of Gaussian noise is that if you have a prior that the data is Gaussian distributed, then after adding Gaussian noise, that you still have that prior. It can be useful in downstream analyses when you're making use of like you're trying to build confidence intervals that encompass not just the differential privacy part, but also other uncertainty from earlier in the data collection phase. Okay. So great. I think I won't dive too much into kind of lower level mechanisms. I think the biggest impact from this talk is the high level APIs. There's a lot of low level details that you can pull out and you can embed in other systems, and you can so there's a lot of flexibility there, but I won't dive into it in this talk. Can I get any questions from people about stuff I was covering today, about applications of DP? Yeah.
Communication.
Yeah.
So I was wondering, when you use computation management, is it not resulting in less accurate visualization or statistics?
Yeah, so this is going back to this bias variance trade-off. When you use truncation, you might be introducing bias because you might be discarding records. But then on the other hand, you are making it possible to make a release in the first place. And you, if your choice of truncation bound is small, then the amount of noise that's necessary to add goes down. So like there's two components of your error. It's your bias and your variance, and you're going to have to choose some choice of this truncation parameter that's going to balance those in a way that's suitable for use case. It might be the case that you have enough data where you can choose a really conservative truncation parameter that will result in more noise being added and no bias, but the noise becomes insignificant given how big your data is. So you got to look for a suitable trade-off between these. Yeah, that's a good question. All right, I'll put through some of this. Plugins. So the library supports Rust, Python, R. You can bind to it from C. And be sure to join the Slack if you have questions, or just send me a message. Always happy to talk through details of your use case.